Hey everyone, welcome to the course. My name is Daniel Nagy, and I'll be your instructor for this 10-week web course called Generative Design, Generative Systems. So I'm the founder of Kaleidoscope.com, which is a consultancy that I founded with the goal of bringing automation and different kinds of technologies to the architecture, engineering, and construction industries. Throughout the years, we've done a lot of consulting for different companies and developing custom software, including the Discover plugin that we'll be learning in this course, and also doing technical training, including webinars like this one. So I'll start with some context for this course and what we'll be looking at. Basically, the context is there's a massive problem in the construction industry. If you look at the past few decades, almost every other industry other than construction has seen a lot of productivity increases. In the same time period, from about the 1970s on, construction has actually seen negative productivity growth. And a lot of the productivity increases in other industries like manufacturing and retail, not to mention agriculture, has been fueled by standardization and automation. And these technologies really haven't made a significant impact on our industries related to buildings. And I would say the main reason for this lack of productivity, or actually decreasing productivity, is that buildings themselves, like every other piece of technology, are always getting more and more complex. And of course, we have now tools and technologies and software that can help capture that complexity. But at the same time, the problem with the industry isn't that we can't represent the complexity of our structures. It's that the process for creating these buildings hasn't really changed in all this time. So we see this big fragmentation in our industries between architecture, engineering, construction firms. And I would say no matter how advanced our technologies get, even though we have BIM and we have all different kinds of software, that problem of fragmentation isn't really being addressed. And that's really what's dragging down our industry and not allowing us to have the same kind of productivity increases and really technological advancement that we've seen in other manufacturing industries. A lot of the advances in other industries that we've seen has been brought about by technological development, specifically around automation. So we've seen in the manufacturing sector the use of automation and robotics to really increase the speed at which things can be built. And you see this a lot with manufacturing of standard kind of products like cars, computers, electronics. And this kind of automation really has been around the automation of physical repetitive tasks. So whereas it used to be people that would build cars, now we have robots doing the same activity in a much better and faster way. And this kind of physical automation really hasn't impacted the architecture industry substantially because most buildings are different. We don't have standard production lines of buildings. Every building is sort of conceived from scratch each time. And even though there's movements like offsite manufacturing, modular construction that are striving to change that, at the end of the day, buildings do need to be more flexible and adapt more to specific site conditions and desires than other kinds of goods. At the same time, when we look at the trajectory of automation and technology, we're really getting into a new kind of technological paradigm where the thing being automated isn't manual repetitive tasks, which we can see as like the first phase of automation, where physical repetitive tasks get automated. Now with artificial intelligence, we're actually starting to develop software and technologies that can start to automate the cognitive repetitive tasks as well. So we have technologies like AI and machine learning, which can actually start to automate some of those things that we do cognitively, but are still repetitive. And because they're repetitive, like they're done the same way over and over again, we can actually train machines to do that work for us. And there's also, based on this new kind of AI technology, there's a whole slew of new startups advertising this ability to actually start to automate a lot of the design process that an architect or an engineer would traditionally do. And I would say the problem with these startups is that, because they're working on automating something, they assume that the design process is always done the same way and always generates the same kind of outcomes. So I would say this kind of automation from outside the industry is a bit dangerous for us as practitioners, architects, engineers, because it sort of narrows down the scope of what we would do. So a lot of what I've been sort of practicing and preaching over the last few years is the need for practitioners in these industries, including architecture and engineering, to actually start to embrace these technologies ourselves and start to make our own custom tools that would bring these AI and automation technologies into our workflows, but in a way that we can maintain our authorship and still make sure that the designs that we create and the workflows that produce those designs are specific to our needs, our interests, and our design vision. So how do we get there? How do we go from where we are today to actually being able to leverage these tools in a way that would boost our productivity as an industry without sacrificing our unique authorship and design vision? Well, in this case, technology can help us. So technology has always had a big impact on the way that designers do their work, of course. A drafting table, a pencil, and a paper are forms of technologies that help us envision and conceive our design ideas and put them into reality. But these days, we have a new kind of technology out there. As I mentioned, we have things like AI and machine learning, which are technologies that don't just capture our design vision that comes from our heads and makes it real, but these are actually technologies that can help us make those decisions and make the decisions on their own. So it's a technology that is becoming less like a tool and more of a kind of creative partner in our design process. And if we look at the current state of AI today, most of the research revolves around what's called machine learning. And machine learning is a kind of algorithm or a process that can train a computer to understand a process by feeding it basically lots and lots of data. So you start with a very generic computational model, and then you show it data that captures the kind of process you want it to learn. And by looking at these data points and trying to make connections between them, these algorithms can learn the patterns in the data that when you feed it a new data source, it can actually make very good predictions or make very good automated decisions based on what it's seen before. So these are the kind of algorithms that are used in a lot of different industries today, including things like autonomous vehicles. And the thing about these kind of approaches is they really rely on having lots and lots of data to train from, and that data needs to be in some kind of well-structured format. So for example, if we want to teach a machine to drive, we start with a very basic kind of generic network, and then we feed it lots and lots of images of objects and what kind of action or reaction the machine, the car, should take based on recognizing those objects around itself. And the thing is, with these kind of models, the computer doesn't know how to drive or how to recognize things on its own. It really is up to us to feed it data where we've already made those decisions. So to teach a car how to drive, we have to give it tons and tons of data about driving and about what it sees in the world around it. And in the case of driving, that's a very well understood system. So we kind of know how driving works. We know what objects you're likely to see. And then based on that data, we teach a computer. And the problem with applying these technologies to design is that we don't really have this kind of well-structured, data-informed way to understand the design process. Like, sure, we can capture data about buildings, right? We can give the computer tons of BIM models of buildings or 3D models or even 2D floor plans. But just showing the computer a bunch of images of buildings doesn't really teach it or give it any information about the design process itself. Like the actual process that the computer took to create those designs from scratch, or like what kind of logic was the computer using to understand how to make those decisions and how to translate the basic needs and desires that an architect would start with into the final form of the building. So we have seen over the years like applications of machine learning for design, but it's really been around this kind of like training computers to create representations of design rather than like doing actual design work. You know, so we can feed like a bunch of floor plans into a machine learning algorithm, and it can produce other floor plans. But I would argue what it's doing is not really designing floor plans. What it's doing is that's producing kind of believable images of floor plans. But whether or not these are good floor plans, there's really no way for the computer to make that decision. So instead of kind of relying on machine learning to create automations in our design work, I've been teaching a different kind of approach, which we call generative design. And here the idea isn't to start with a kind of generic model and a bunch of data about how our design process turns out. The idea actually is to create your own models, which are very specific to your own design process and the models and the kind of problems you're trying to solve. So I would argue that, you know, these days, designers working today to leverage AI, they must build their own automations. That we can't rely on the software industry and the technology industry to give us automation tools because those kind of tools are very likely to be very generic and not really capture our own needs. Instead, we have to learn these technologies ourselves and apply them to create our own kind of intelligent models, which can enable those automations for our own work. So how does this generative design process look like? Well, in general, it's composed of 3 different components. So these are the kind of basic steps that you have to take to enable this automated process within your own design workflows. And the first step of this process we call generate, and that's really nothing that much different than parametric design. So this parametric design is a kind of foundation, the bedrock of generative design. And parametric design, or creating computational parametric models, allows you to define for the computer how your design systems work. So whatever design problem you're trying to solve, you as the designer has to tell the computer how that problem in general is solved. So you can think of it as kind of creating a template or a kind of description for the computer, not of how to create one specific solution, but in general, how these types of problems can be solved. So these models are called parametric models because they expose a set of parameters or data or numerical values that control a model, and that model is actually able to create a variety of different solutions to the same problem. So for example, we'll see later in the course, we can create a model to divide up a floor plan of an office building to create a bunch of different rooms and desks. So when you make a model like this, you're not saying, okay, here's the exact layout of the office space. You're saying, here is how I can represent a process which takes a boundary of an office space, and that boundary can change in different ways for different buildings. And here's how I can kind of structure a process for dividing that office space into smaller components. And each of those decisions, like how that space is divided into how many spaces and what their functions are, you can set as parameters. So those things can actually vary. So this kind of parametric model creates what we call a design space. It's not a single design option, and it's not like several design options as we're used to doing. It's actually kind of space, like a conceptual territory of tons of different potential design options, potentially even infinite number of design options. And the thing with generative design is once we craft that kind of design space, we don't have to worry about picking a design option from that space. We can actually use algorithms to automatically search for that space and give us the best designs or the most interesting designs, or just a variety of different designs for us to explore. Now the question is, if we create this design space, and we use these algorithms to search through it, how does the algorithm know which direction to go? How does it actually know how to explore the designs and which designs are best? Well, to do that, we have to give the computer some information and a way to evaluate each design option that's coming from the generative model. And this we call the second stage of generative design, evaluate. And here we can rely on a lot of different kinds of simulation algorithms. So the way that we evaluate these models, could be very simple, like in the office layout example, if we're placing desks in the office, part of the evaluation could be meeting a certain number of desks as a requirement. And that's very simple to calculate. We can just count them in the model. But some things we want to evaluate in our designs are more complex. And here we can actually use like more sophisticated simulation algorithms to analyze things like structural performance, daylight analysis, shadows, other kinds of sun studies, even views. And these kinds of simulations are exciting because they allow us to evaluate our models in a way that wouldn't really be intuitive to us. And if we hook up these simulations to these automated optimization algorithms, they can actually steer and discover design solutions within our design space that perform very highly in terms of the goals of our design, and actually discover solutions that we may not have even thought of intuitively on our own. So once we have a parametric generative model that can create tons of design options for our problem, and we hook it up to a bunch of evaluators that can tell the algorithm which designs are better or worse, we can connect this kind of model to an optimization algorithm to actually do that automated search and exploration. So this is a kind of conceptual diagram of a design space model. And creating design space models, these parametric models that generate design options and evaluate them, is really the biggest task of generative design. This is really like, as a designer who's using generative design, this is really what you'll be doing. And this is what we'll be studying a lot in this class. How to create these models, number one, and what are all the different strategies that we can use for creating these models. And then also like thinking about what makes a good design space model. It might seem that you don't have to make a lot of decisions when you're designing these models because the algorithm is the thing that's actually finding the designs for you. But it's really important to understand that the algorithm can only find designs that are specified within the parameters of your design space. So it's critical that you understand how to design these models and even how to evaluate which models are good and which models are more likely to yield the best results. But in general, this is kind of what one of these design space models looks like. You start with a set of inputs. So these are numerical inputs usually. They can range numbers within a certain range, or it can be like selecting from a set of different options. And those inputs all go into the model, which creates, based on those input settings, a unique solution to your problem. So this is a kind of simple bridge example that we'll look on at the end of this session. We have 11 different inputs to control everything about the geometry of this bridge. So we have 6 inputs that control the height of each of the structural members. And we have 5 inputs, which we call categorical inputs. These are choosing from a set of 4 different structural configurations for each structural bay of this bridge. And we'll look at more of the different input types, continuous, categorical, sequence, later when we get into learn and discover. So based on these inputs, we create a unique design from our design space. And then we pass that design to some kind of evaluation. Here we're using structural analysis software to actually evaluate for every design that's coming from that design space, the weight of the bridge, the displacement or the stiffness of the bridge, and also the stress utilization. So these outputs are the way that the algorithm will know which bridge designs that it's producing from the inputs are better than the others. So on its own, this design space model creates a way for the computer to generate tons of different design options. But if that's all it did, it wouldn't be very useful, right? And we know these kind of parametric models already. usually we create these models and we play around with them to create different options. But if we ask the computer at this point just to use that model to create lots of different bridges, there's a potentially infinite number of solutions, and most of them are probably really terrible. But the key to generative design is that once we have the design space model specified, we can actually use intelligent algorithms, like the genetic algorithm in this case, to automatically take that model and start to play with it, but play with it in the way that it's learning from its experience playing with it, and can generate better and better solutions over time. So if we take this model and plug it into a genetic algorithm, you can see that here we're combining images of designs that the algorithm is exploring over time. So genetic algorithm works through generations. It actually optimizes based on looking at sets of designs in order. And here's the first generation. It starts by looking at a certain number of random designs. You can see there's like a huge variation in these designs and what they look like. But then over time, as it keeps generating designs and learning more and more about which ones perform better in those evaluation metrics, you can see it starts to kind of narrow in on the best design and ends up kind of converging on this design of something like, we would intuitively think would make a good bridge. It's got that kind of curved catenary shape. But it's important to remember that the algorithm doesn't know anything about structural analysis or structural design. It doesn't know what a good bridge should look like. It's actually deriving this shape entirely from working with this design space and just looking at how do I control the input parameters and what kind of designs I'm able to generate and how they perform. So what we'll be looking at in this class is both techniques and strategies for working with parametric models to create our design spaces. And for that, we'll be using Grasshopper, which at this point is like a pretty popular parametric design, computational design platform. It's very popular with architects and now even with engineers. It's a very flexible platform, and we can use it to create all kinds of different design space models for our particular interests. And so we're going to use Grasshopper to create parametric models that define a set of inputs, can generate lots of different design options. And we're also going to use Grasshopper to evaluate those design options across different criteria. Now, for the last piece of the generative design process, the optimization piece, we're actually going to use a different design tool called Discover, which is a plugin for Grasshopper that I've written over the last few years. And Discover is just looking at that optimization process. The idea of Discover was not to create like a new design tool for optimization. It was just to plug into a tool that lots of people are already using and just provide that kind of optimization process on top of it. So we'll be using this tool to run automated optimizations on our models. And Discover is in two parts. The first part is a library for Grasshopper, which comes with a small number of components that plug into your model and connect your model to Discover and specify like what kind of inputs and what kind of outputs your design model uses. And once you connect your design model to these components, there's the other part, which is the Discover interface, which you see here on the left side. And this is the interface that's going to let you run the optimizations and visualize your design spaces, select the best performing designs, and even send those designs back into Grasshopper. So I'm going to end today's session with a demo of actually starting up Discover. You can find instructions for installing it and getting to work with Grasshopper online. And we'll see a small demo of actually like opening up Discover, plugging into this bridge example, and getting it to run. Okay, so here you see a quick kind of sped up demo of what we'll see later in the session. You can see here we've connected the bridge model to Discover. We've started running the optimization, and now you see over time, Discover is actually creating different design options, and it creates hundreds of different options, but it's doing so in a way that's actually targeting and pinpointing the goals of our design. So in this case, we're looking for the stiffest bridge with the least weight. and you can see that how those designs start to converge on that kind of good high performing design option.